This rusted gear shaft hasn't turned in years, crippled by severe scoring and deep wear. Today, one mechanic begins the restoration starts not with rebuilding, but with aggressive subtraction. A hydraulic press delivers tons of compressive force to sever the rusted section. Breaking the seized joint cleanly is critical. Any compromised steel left behind would invite immediate fatigue failure. The shaft moves to the lathe. After clearing away the deepest surface damage, the craftsman introduces a fresh steel sleeve to bridge the gap. Mating new stock to old carbon steel requires intense, localized heat. The welding arc easily clears 3,000 degrees Fahrenheit, liquefying the contact points and creating a unified molecular bond. This initial pass isn't just about sticking parts together. It acts as an anchor for the heavy rotational loads the shaft will eventually bear. Allowing the piece to rotate on the chuck guarantees an even distribution of thermal stress, preventing the steel from warping as it rapidly cools. The foundation is set. Once the rough welds have cooled, the true shaping begins. The cutting tool shears through the hardened steel, stripping away uneven excess in continuous, tangled ribbons. This steady material removal is dictated by strict tolerances. If the feed rate is too fast, the tool chatters and ruins the surface finish. Too slow, and it merely rubs against the metal, generating excessive heat without cutting. The blue tint in the metal shavings reveals the extreme temperatures generated right at the shear point. By maintaining a constant, deliberate speed, the mechanic ensures the cylinder remains perfectly concentric, setting up the exact dimensions needed for the structural sleeve.
Tick, tick.
As the tool post advances along the bed, the heavy scoring is replaced by a bright, pristine finish. This final shaving pass removes merely thousandths of an inch of material. Precision turning is essential here to prevent any high spots from causing extreme friction within the machinery housing. A smooth surface reduces wear on internal bearings and drastically extends the working life of the moving components. The rhythmic hum of the lathe confirms a consistent depth of cut. Machining relies on objective measurement, not estimation. The mechanic uses a micrometer to verify the shaft's diameter down to the microscopic level. Even a slight deviation could render the entire assembly useless under industrial strain. A final, shallow pass locks in the required dimension, leaving behind a perfectly uniform steel canvas. The heavy lifting of the repair now transitions into structural assembly. Following a deep reaming process, the newly machined cylinder is press-fit directly into the heavy rusted gear housing. This interference fit provides the initial mechanical lock, ensuring zero internal play between the two mating components. The mechanic carefully presses the fresh steel home, checking that the shoulder sits completely flush against the heavy iron face. Any misalignment at this stage would introduce catastrophic vibration once the assembly hits its operational RPM. Using the lathe chuck as a stationary jig, he dials in the concentricity one last time. Every measurement must be flawless before permanent heat is applied. The micrometer confirms the alignment is dead true. With the geometry locked, the mechanic prepares to fuse the components with a heavy structural beam, bridging decades of wear with newly hardened steel. The union becomes permanent under the intense glare of the welding. Fusing thick, high-carbon gear steel to a standard milled shaft is a demanding metallurgical process. The operator lays down a thick, continuous bead of molten metal, filling the chamfered groove between the two distinct alloys. Penetration is everything. If the weld only sits on the surface, the immense torque of the gearbox will shear it cleanly off within minutes of operation. By weaving the electrode back and forth, he ensures the liquid pool bites deeply into the root of the joint. The extreme heat inevitably causes the surrounding metal to expand, which is why the assembly remains clamped rigidly in the chuck. A secondary pass adds necessary mass to the connection, reinforcing the joint against heavy lateral shocks. As the slag begins to cool, the shaft and gear behave as a single, indestructible unit. Raw welds are strong but dimensionally unstable. An angle grinder aggressively knocks down the high crowns of the cooling bead, bringing the dense material flush with the shaft's profile. Any protruding weld splatter could catch on surrounding seals or bearings during rotation, causing massive internal damage. Hand filing the gear teeth follows the heavy grinding. This manual step removes sharp burrs left behind by the heat and abrasion, guaranteeing smooth engagement when the gear meshes with its counterpart. The file follows the involute curve of each tooth, restoring the exact geometry needed to transfer power efficiently without binding. It is meticulous, repetitive work, but avoiding premature wear on the drivetrain makes this localized finishing absolutely essential. The final layer of security comes from a mechanical fastener. Cutting fresh internal threads with a T-handle tap requires patience and ample lubrication, keeping the high speeds from snapping inside the bore. Once the threads are established, a locking bolt threads deep into the shaft, permanently compressing the assembly together. The lathe is fired up for one final pass across the mated surface. This skim cut guarantees that the gear, the weld, and the shaft all share the exact same axis of rotation. Eliminating runout ensures the heavy unit will spin quietly and true, drastically lowering the risk of bearing fatigue over its operational lifespan. The polished surface is proof of perfect alignment. High-grit abrasive paper brings the restored surfaces up to a mirror polish. This isn't done for aesthetics. A highly polished steel surface possesses fewer microscopic peaks and valleys, which directly reduces friction where the shaft interfaces with its heavies oil seals. Less friction means lower running temperatures and a seal that will last years rather than months. The spinning metal blurs under the light as the final abrasive layers strip away the microscopic scratches left by the turning tools. Releasing the massive assembly from the chuck reveals the full scope of the transformation. Every pass of the lathe and the welding rod was a deliberate step away from the scrap heap. What began as a seized, deeply gouged lump of iron has been painstakingly reconstructed into a precision power transfer component built to exact tolerances and ready to handle massive industrial torque.
मजाक ना करो।
With the primary gear repaired, attention turns to fabricating a missing internal hub component from solid bar stock. The cutting tool digs aggressively into the fresh cylinder, shedding thick, blue-tinted steel chips. That coloration is a direct byproduct of the fierce friction heat escaping into the waste material rather than warping the core workpiece. The heavy feed rate rapidly reduces the outer diameter, roughing in the basic dimensions before the delicate threading operations can begin. Keeping the cutting edge heavily engaged prevents work hardening, allowing the machinist to quickly shape the raw metal into a specialized structural component. Working from solid stock guarantees maximum tensile strength, free from the hidden casting flaws that often doom mass-produced parts. The steel surrenders its shape. After facing the cylinder, a rigid center drill establishes a pilot hole perfectly on axis. Starting with a short, stiff bit prevents the tool from wandering across the smooth metal face as it bites. The lathe maintains constant rotation, feeding the metal into the stationary drill to ensure the internal bore remains dead, true to the outside diameter. This initial cavity clears a path, reducing the cutting friction for the larger boring bars that will follow. A perfectly centered hole is the foundation of any balanced rotating assembly. The newly machined hub meets the gear face for the final structural fusion. The welding electrode strikes, creating a blinding pool of liquid steel that bridges the two heavy components. Maintaining a slow, steady travel speed gives the molten puddle time to consume the root of the joint, preventing hidden voids. As the smoke clears, a dense, uniform weld bead locks the assembly together. The intense thermal bond solidifies into an unbreakable mechanical hold. A drill press bores the final locking pin hole directly through the new hub. What was a ruined, seized scrap pile is a working drive component again, revived, heavily fortified, and structurally sound. Every hidden detail they cut and welded is what its reliability now rests on. A machine this robust doesn't die. It just waits to be rebuilt.